Okay. Hey, everyone. Welcome back. My name is Chanel Hasten. I'm the Director of Outreach and Community Relations for the Elakha Alliance. And next up, we have another wonderful presenter for our Sea Otter Science Symposium. I'm going to pass it off to Bob Bailey, our Board President for the Elakha Alliance, to introduce Joanna.
Thank you so much, Chanel, and thank you, Joanna, for being here. I saw Joanna give a presentation, I think it was to the Ocean Policy Advisory Council, or maybe it's the Ocean Science Trust. That was it, a few months ago, and I just thought, oh, bingo. The Elakha Alliance, as an organization, has been trying to get its arms around the concept of blue carbon and how sea otters fit into that. And so when I saw Joanna's presentation, I thought, well, this is a good start. So I'm really pleased you can join us today. Joanna holds a master's degree in science from the marine biology and biological oceanography from the University of Oregon. And I assume that you did a lot of your work at the Oregon Institute for Marine Biology out in greater downtown Charleston. She has been an Oregon Sea Grant Natural Resources Policy Fellow, working as a Blue Carbon Fellow for the Nature Conservancy. Her work is a general exploration of how blue carbon pathways operate in Oregon's coastal ecosystems, both marine and estuarine, as well as some of the interconnections with the terrestrial environment, and how they may contribute to the state's greenhouse gas reduction goals, and a discussion of currently who is doing this work. So that's what I've got on my list here. She may have an entirely different presentation. So Joanna, thank you so much for joining us today and talking to us about blue carbon on the Oregon coast.
Thanks so much, Bob. Let me share my screen. I'll kick you off screen share. Okay, can you see?
Yep.
The screen? Great. What I like to hear. Thanks so much for that introduction, Bob. I was really pleased to get an invitation to share my work today with you all. This has been, ongoing work. There's been a lot of hands in this work, and it's been really exciting to dive into this kind of new-ish area of thought, of research, and discuss how what the opportunities are for Oregon. So about a year ago, I started an Oregon Sea Grant Natural Resource Policy Fellowship with the Nature Conservancy. And the focus of this fellowship, as Bob said, is an exploration of Oregon's blue carbon as a climate strategy. There's a number of individuals who have been working and thinking about blue carbon. And these collaborative efforts are aimed to give full consideration to, carbon that we see on the coast, on the nearshore systems that are placed alongside terrestrial natural climate solutions. I was really excited to hear the keynote this morning. The elevation of the work that nature does and our responsibilities to steward it and enhance the way that nature can provide these benefits is really kind of the driving thought behind this work. And he put it way more eloquently than I could. So I really appreciated those words from him. So to give kind of a background of where I'm coming from, I received my bachelor's in biology from U of O, and then continued on for my master's at the Oregon Institute of Marine Biology here in Charleston. And as Bob said, I currently live and work in Coos Bay. I've been here for a few years now. I really like it. So getting away from carbon a little bit, I think I'm going to connect my graduate work to kind of my thinking about carbon and carbon cycling in the ocean. But my graduate work actually focused on the vertical migrations of pyrosomes. These are planktonic jellies, they're tunicates, that became hugely abundant off the Oregon coast several years ago following that marine heat wave. We heard about the blob in several talks already today. So this explosion of this jelly species kind of coincided that heat wave. And so without getting too far into the details of that work, pyrosomes are like several other kinds of oceanic animals who stay in the dark depths of the ocean during the day to avoid predation, and migrate to the productive surface waters at night to feed. And the daily migration of these animals from the ocean surface to depth creates connectivity among vertical ocean zones and facilitates transfer of carbon to the deep sea. So they feed at the surface at night and then migrate down to the water, to the deep waters, and then, defecate. Additionally, when you get these mass blooms of jellyfish, they're followed by mass die-offs, and that can contribute huge amounts of carbon to oceanic sediments. So although my master's work wasn't focused on carbon dynamics, it drew me to this fellowship opportunity to explore the natural processes that result in carbon sequestration in coastal and marine environments, including the way that we as humans have disrupted that piece of ecosystem function. So just to give you a brief overview of the structure of my talk today, I'm going to go into just like kind of a broad kind of basics of natural climate solutions and blue carbon, and then talk more specifically about blue carbon in Oregon, the ecosystems that are specific to this region. I'll talk briefly about my fellowship goals and products, but the bulk of my talk today is going to be on a report that me and my colleagues have been working on, this blue carbon science synthesis for Oregon, which includes discussions of coastal and marine blue carbon, as well as kind of other pathways that we're thinking about, including seaweed and shellfish aquaculture and marine vertebrates. So natural climate solutions, or NCS, there's also mentioned this morning as nature-based solutions, or NBS. The terminology is a little confusing, but the way that I tend to, the way that it appears in discussions most often in the spaces that I'm in is natural climate solutions. So these use ecosystem restoration, conservation, and management to reduce the amount of greenhouse gases like carbon dioxide and methane in the atmosphere, while also providing co-benefits that maintain or improve biodiversity and ecosystem services to benefit coastal communities. These can be things like coastal shoreline protection, water quality. There's a lot of different kinds of services that can be provided. Coastal and marine ecosystems, they're already doing a lot of work. The ocean is our lungs, as the keynote speaker mentioned this morning. So they're already doing the work to sequester a large amount of carbon dioxide. And in those natural processes, some carbon is also released as part of the normal ecosystem processes. But when we develop and degrade ecosystems from the things that humans do, those degraded ecosystems may emit more greenhouse gases. And restoration projects can actually restore important ecosystem services, resulting in increased sequestration. The graph I'm showing here shows the carbon stored or sequestered over time following a restoration project. The gray dotted line represents the slow rate of carbon storage in a degraded ecosystem, and the green line shows the increased rate of carbon storage as a result of restoration and restored ecosystem functionality. The difference between those two sequestration rates is the carbon benefit, or sometimes called the additionality if you're used to carbon market speak, and that increases over time from the time of restoration. Additionality is an important concept in climate change mitigation, and it's used to distinguish the net climate benefit associated with an activity or project from what would have happened anyway in absence of that activity. So you're comparing the carbon benefits to a baseline or business as usual. Blue carbon is one example of a natural climate solution, and it refers to the carbon stored and sequestered in living vegetation, soils, and other biomass in coastal and marine ecosystems through natural processes. And when we think of global estimates, they suggest that restoration and conservation of blue carbon ecosystems could sequester the equivalent of 3% of annual global emissions in the coming years through limiting that ecosystem degradation and conversion and restoring disturbed ecosystems. So when we're thinking as a global strategy, it can have, it can have an effect It's not the only tool we have, nor should it be, but it is something that we can use in our toolkit. So to kind of think about how carbon flows through and is stored within ecosystems, I'm showing this graphic. This is a generalized figure of a coastal ecosystem. This is not one that I would say is representative of Oregon blue carbon. We don't have mangroves. That's shown on the left. But the arrows on this figure show the uptake and release of carbon dioxide. So the purple is the uptake of carbon dioxide from the atmosphere or from the ocean for plants to use in photosynthesis. And some amount of carbon dioxide is also released as a result of that natural respiration. The red arrows here show the storage, the long-term storage or sequestration of carbon dioxide within soils via accretion or within woody biomass, as in the case of those mangroves. And the balance of that sequestration, or that uptake versus the emissions, determines whether an ecosystem stores or emits carbon dioxide. And those sediments, once it's stored in place, it's a relatively permanent carbon sink as long as that ecosystem function is maintained. So accounting becomes a really important part of how we measure the benefit of a blue carbon ecosystem. Oregon's temperate coast is unique. I'm sure anyone who has been to the Oregon coast knows that. Excuse me. The strong northern winds that we get along the coast in the summer drive a process called upwelling, where those nutrient-rich waters are pulled close to the shore, and it fertilizes, an incredible diversity of life. Coastal plants and seaweeds and kelp, they're all fueled by these natural fertilizers, and they pull carbon dioxide out of the atmosphere into living biomass, where it may be consumed by animal grazers and incorporated into those coastal food webs, or stored over time in soils and sediments and living biomass or in woody biomass. The long-term storage of atmospheric carbon within these sinks is really the basis, again, of carbon sequestration work. Historically, the bulk of blue carbon science, it's not an old field, but it has mainly been studied in the tropics, focusing especially on mangroves and seagrasses. But there has been a fair amount of work done in the Pacific Northwest recently, as it's gained attention for resources and research. And again, tidal wetlands and seagrasses in our estuaries have been the primary area of focus due to the ease of access for study and existence of carbon standards and methodologies. But it really is important to consider that other carbon pathways outside of the estuary have the capacity for producing, storing, and sequestering carbon. We've heard a lot of talk about kelp forests and marine vertebrates like whales, producing, storing, moving carbon. And so part of this fellowship work is to explore those adjacent or unrecognized opportunities for blue carbon. And we're just trying to, ask some questions, see where it leads, and see what is or is not worth pursuing. I want to make a quick note on offset markets. So these conservation activities that lead to climate mitigation via blue carbon may include carbon projects developed as part of an offset project. And those carbon credits are measurable, verifiable emissions reductions resulting from or that aim to reduce or avoid greenhouse gas emissions. Blue carbon projects don't necessarily need to be enrolled in a carbon offset program to generate a real climate benefit, but they do need to be enrolled if the project developer wants to sell those carbon credits. It can be used to fund additional conservation stewardship, but that's a consideration. However, not all blue carbon activities are necessarily able to be enrolled in an offset program because of the lack of verified methodologies. Like we don't have any methodologies for kelp, and because it's so hard to track where the carbon ends up. So right now that's not on the table. The verification process can be intensive. It takes a lot of time, and it's not necessarily guaranteed if you're starting a carbon project. And there was a feasibility assessment done last year where researchers concluded that there are real greenhouse gas removals from our estuaries, from estuary projects, but under a certain size, the costs really outweigh the benefits. And being the cost or the revenue generated by those carbon offsets. And in Oregon, the lack of emissions data is really a big gap. And measuring those fluxes and determining what a baseline is to set up that carbon accounting is really critical for blue carbon offset projects. My work isn't really focused too much on the verified carbon market, but I wanted to acknowledge that it exists. So to kind of go over my fellowship goals, blue carbon it was a term coined in 2009, so it's a fairly recent area of study. There's a lot of active research happening and creative thinking, and blue carbon science is evolving really rapidly, but many stakeholders still remain pretty uncertain about how to incorporate blue carbon into their strategies for coastal management. The broad goal of my fellowship has been to explore blue carbon possibilities as it relates to Oregon specifically. Conversations surrounding natural climate solutions in Oregon has focused on the terrestrial side, like forest carbon. And the team that I work with hopes to elevate the important work being done in highly productive ecosystems on Oregon's coast. We're also speaking with people working in or adjacent to the blue carbon space, such as in research, monitoring, restoration, advocacy, policy. And these conversations result in spiraling connections to other stakeholders, and we're trying to document partners and opportunities to work together. Through this work, we'll have a better understanding of the knowledge base and potential for blue carbon work on the Oregon coast, and hoping that it will help better facilitate on-the-ground action. So the 3 fellowship products will be the science synthesis report, what I will be talking about mostly in the coming slides. A stakeholder snapshot showing ongoing work and opportunities. And the third is we're contributing to the development of methodologies to conduct a statewide inventory for blue carbon. So to help interested stakeholders make sense of this evolving opportunity surrounding blue carbon, my colleagues and I at the Nature Conservancy in Oregon compiled this document to examine the status of blue carbon science in Oregon and the Pacific Northwest. Well, the science comes from the broader region, and it's applied more specifically to Oregon. And it summarizes that regionally relevant literature to help readers understand the basics of blue carbon cycle and greenhouse gas mitigation and the mechanisms of carbon sequestration in Oregon's coastal and marine ecosystems. With this document, we're aiming to highlight what's known and what remains unknown concerning coastal and marine blue carbon in Oregon, and provide some recommendations for managing blue carbon. We're also summarizing the gaps and uncertainties and opportunities for various types of blue carbon, as well as those next steps. So the 2 major buckets of how I think of blue carbon in Oregon is coastal and marine, in the estuaries and on the near shore. So coastal blue carbon includes estuarine wetlands, like scrub shrub and forested tidal wetlands. These can be, thickets of shrubby vegetation to Arctica spruce swamps. It also includes tidal marshes, and submerged aquatic vegetation like seagrasses or eelgrass that we have here, and any seaweed that's in the estuary, as well as tidal mudflats. Marine blue carbon is a nearshore ocean ecosystems, mainly subtidal kelp forests, but also the associated species like marine mammals and other open ocean biomass. So I want to go through the different ecosystems and kind of the basic findings of how they function in terms of carbon and any data and research needs. So in tidal wetlands, carbon is produced through photosynthesis. Again, that's always going to be the case for any of these producers. So they're absorbing carbon and storing them within their woody biomass, if that's the case, or by accreting soil, so building up soils, and accumulating, dead plant matter that's stabilized by those root systems. The capacity for carbon storage varies among wetland types. Carbon stocks appear to increase with elevation, with the highest stocks associated with spruce swamps, which are highest in the estuary. One complication within wetlands is that carbon benefits from sequestration may be offset by greenhouse gas emissions due to lower salinity. So under lower salinity conditions, there tends to be an increase in methane generation, which is a really potent greenhouse gas. So there's studies underway to look into this question, into where we see high rates of emissions, and be able to measure that balance. In tidal wetland restoration, restoring that salty tidal flow to the diked, disconnected wetlands has a really strong climate benefit by reducing those potent methane emissions. So, the two activities we have is lowering emissions and raising sequestration. So restoring tidal flow is a great way to lower emissions. Tidal wetland forests have gained a lot of attention because of their high rates of carbon storage. The carbon stocks within forested tidal wetlands are on par with tropical mangroves and Oregon's old growth forests. So it's a really high bang for your buck. But much of their historic extent has been lost due to soil subsidence and difficulties in restoration. Those scrub shrub wetlands are recently gaining more attention too. There isn't as much research on them, but they appear very promising, although we're still lacking some data. The vast majority of Oregon's tidal wetlands have been lost or undergone some kind of change due to diking and vegetation conversion. But there's a long history of coastal ecosystem restoration on this coast with tremendous co-benefits. So I'm lumping all of these tidal wetlands together, which, because I just don't have time to go into each one individually. But that's kind of the big overview of tidal wetlands. Eelgrasses are also sometimes included in tidal wetlands, but I wanted to discuss them separately. So Oregon seagrass is primarily eelgrass. There are also some surf grasses, but not much is known in terms of their carbon contribution to blue carbon. And like salt marshes, eelgrasses occur pretty low in the estuary. They're often submerged. And this carbon storage mechanism is pretty similar to other tidal wetlands by stabilizing sediments. The eelgrass beds in the Northwest have lower carbon stocks and sequestration rates relative to tidal wetlands, but their emissions rates are also probably lower because of that higher salinity. The carbon storage can be pretty variable depending on local site characteristics, including the sediment load and hydrology. So site-specific data are really needed. And there's a pretty high connectivity between eelgrass and terrestrial and subtidal habitats. So much of the carbon within eelgrass beds isn't produced by eelgrass itself, but it's imported into the system, and the eelgrass stabilizes that sediment. So this isn't great in terms of carbon credits, because in carbon credits you have to, they require it to be produced and stored within this ecosystem. But those standards necessarily understate the carbon services of eelgrass because of the network of connections to other ecosystems like nearshore seaweed. And eelgrass experiences these cyclical losses that we heard about earlier today, and they're sensitive to marine heat waves. So we still need to identify what's driving eelgrass loss and and work on better mapping of historic and potential extent. So when it comes to wetlands, Oregon has among the best quality and quantity of coastal blue carbon data. This graphic of blue carbon data across the US coastal states is helpful to compare the status of Oregon's data sets relative to other states. So Oregon's in a pretty good position to begin answering important questions about how blue carbon contributes to statewide climate mitigation. But as you can see on this graph, habitat coverage is kind of the weakness. And I will also say that even though relative to other states that we have a pretty, we have among the best data, those data are still sparse. But these data gaps are rapidly being filled, and much of that work done by the Pacific Northwest Blue Carbon Working Group and others are answering those questions and are likely going to be addressing them by the end of next year, which is really exciting. And part of that work includes measuring carbon stocks, sequestration rates, and gas fluxes within natural or undisturbed tidal wetlands and disturbed wetland types. Improved mapping of the current and potential extent is needed for more refined estimates of carbon production and sequestration. This applies to all the wetland types. And it's important to identify blue carbon restoration areas at that local scale. The accuracy of eelgrass, so eelgrass mapping, my understanding is that it's not highly refined across the coast, and the accuracy of scrub shrub and forested tidal wetland extent needs to be improved as well. So there's an ongoing collaborative effort to pilot a method to refine these maps of blue carbon and identify restoration sites actually within the Coos and Yaquina estuaries, with special attention paid to those scrub shrub and forested tidal wetlands. And eventually this work will be scaled up coastwide. And in addition, it's also important to monitor the changes of this extent over time, because as we see, sometimes the habitats flux. So moving on to marine blue carbon, which is a little bit more appropriate for this venue. I'm talking a bit more about nearshore kelp forest and the associated fauna. So we've heard a lot about kelp already this afternoon. And seaweed and kelp are of a pretty recent interest as a source of blue carbon. So seaweed functions differently in terms of blue carbon. Whereas in the estuary, the biomass and sediments accumulate in place. Kelp forests are not like that. And to get carbon sequestration, that biomass, we lose kelp on a kind of a yearly basis. It floats out to sea, it gets shredded up into tiny pieces. So the sequestration doesn't occur necessarily in nearby sediments, but has to travel way offshore and sequestered in the deep sea within oceanic sediments, or potentially in the estuary. I don't want to go too much over this. We know that kelp and seaweeds are macroalgae, and they're like marine plants. They use sunlight and dissolve CO2 to photosynthesize. And depending on the species, especially those canopy forming bull kelp, they turn over on a fairly short basis, yearly or biannually. And large, robust species like kelp are more resistant to grazing and decomposition, which is important in terms of carbon export because it slows the rate of decomposition. So more of that carbon makes it to carbon sinks. It's even suggested that a quarter of the carbon stored within eelgrass meadows is of seaweed origin. In terms of seaweed carbon, there's really a lot of unanswered questions, and Oregon seaweed studies are needed in terms of understanding the extent of canopy kelps and their fluxes over time. So it's great that there's some kelp survey works happening. And then we also need to know, their growth rates and carbon export rates to be able to figure out how much kelp contributes to ocean carbon sinks. And kelp forests are complex. There's been some studies saying that we need to know all of the inputs and outputs to really understand the magnitude of impact of seaweed on blue carbon sequestration. And this work is really important given that Oregon kelp forests are vulnerable to marine heat waves, herbivory, and human activity. So to understand how much carbon benefit is lost, we need to know how much is produced, the rate of production, the rate of sequestration from our kelp forests. So those exploratory studies to understand carbon fluxes within nearshore seaweed beds are really important. And how kelp forest restoration can benefit additional carbon storage, in addition to, of course, the many other co-benefits. The ocean carbon cycle is really complex, so I wanted to show this graphic of the interactions of large marine fauna interacting with one another and their environment to affect the movement of carbon. And this is a simplified graphic. I feel like it's too much to throw at you, but this is just only a few pieces of the avenues by which carbon moves among the different ocean zones. So the net effect on atmospheric carbon depends on the relative rates of production, consumption, respiration, and burial. So there's, trophic cascade carbon that we heard about before, of the movement of carbon among of participants of a food web. We heard about the whale pump moving vertically and fertilizing these phytoplankton blooms at the surface, carbon stored within biomass and stored drawn down to the ocean floor through deadfall carbon. So these animals can play a direct or indirect role in the carbon cycle of the nearshore ocean. Long-lived ocean animals like whales or even some fish species store a fair amount of carbon within their living tissues. I think Ralph this morning said it was on the order of, tens of tons in a whale. Other marine animals may positively affect blue carbon through indirect action as well. I had to throw in a sea otter example, but there's evidence that the presence of seawaters in a kelp forest has a significant indirect impact on the net primary production, and that production leads directly to carbon sequestration. Whales, again, may fertilize those phytoplankton blooms and the subsequent carbon production from phytoplankton by, bringing nutrient-rich fecal matter to the ocean surface. So from a carbon action perspective, identifying management levers is really critical in order to affect the direct and indirect carbon benefits from these nearshore oceanic ecosystems. Managing marine fauna as a carbon resource is pretty complicated, and there's no clear precedent. Whales and fish, as we know, are mobile. They're not constrained to a particular location. Whales may migrate hundreds to thousands of miles, and they cross a mosaic of management jurisdictions. So policies and programs targeting fish carbon, it's unlikely to be effective without coordination among regional partners. And identifying candidate resident species might be one option by focusing on Oregon's jurisdictional waters. And that's a necessary first step to include the biomass carbon of these marine species in state level policy and management decisions. Importantly, managing marine faunal pools, so these oceanic animals, managing for carbon would include activities that likely will intersect with fisheries, and those socioeconomic impacts are uncertain at this time. The impacts depend on the policies, and there's no clear, at this point, there's no clear direction for what policies would be effective for carbon management. So moving on from our traditional coastal and marine blue carbon, and I will say folks sometimes want to separate that the whale carbon, the biomass carbon out from blue carbon. That's kind of an ongoing discussion. But I want to talk about the benefits of potential benefits of conversations that I'm hearing surrounding marine aquaculture, mariculture, and mariculture refers to the cultivation of marine species and has been proposed as another opportunity for climate mitigation on the Oregon coast. But the mechanism of climate benefit here is slightly different than that of place-based blue carbon ecosystems. And it relies much more on emissions reductions instead of direct sequestration, especially because these are products that we're growing for consumption. And so, except for carbon that is released while during the production phase back into the ecosystem, those products that are grown, the carbon ends up, being re-released to the atmosphere. Seaweed is one particular area that has been suggested for carbon production. It's cultivated globally for food and other products, and it can be cultured either within tanks or in the water on anchored lines. It can be a relatively inexpensive and nutritious and delicious food source. But seaweed production in Oregon is in its pretty early stages. Another Sea Grant fellow that I work with is actually working to understand the market potential for seaweed in Oregon. Seaweed production is gaining more attention in the Pacific Northwest for potential climate benefits, as I said. And certain species may be more cost effective due to high growth rates and carbon content. But realistically, it seems that seaweed farming is likely to play a fairly small role in sequestering carbon, and should probably be considered only one of many tools and strategies. As an agricultural product, farmed seaweed doesn't appear to have these direct long-term carbon sequestration benefits that we would see in blue carbon ecosystems. But seaweed farming might have indirect benefits, like if you're replacing a carbon-intensive product with a seaweed product that has a much lower land use and carbon emissions than that product produced through traditional agriculture. And it's not to mention that the total emissions from seaweed production, including the transportation costs, which is usually a pretty big fraction of the total emissions, that's a small fraction of emissions associated with other types of production, like fish aquaculture, for example. There's also opportunities for restorative aquaculture of native seaweeds that may have multiple environmental benefits, including improving water quality, reducing excess nutrients, buffering ocean acidification, and seeding wild populations. But there's a pretty substantial amount of research that needs to be done to understand the balance of benefits and potential negative consequences of seaweed aquaculture, in addition to clarifying the magnitude of those carbon benefits. So the last thing I want to talk about is shellfish aquaculture. This is one of the questions I actually got in my presentation to the Oregon Ocean Science Trust is how cultivating shellfish like oysters, mussels, and clams contributes to carbon sequestration benefits from the production of a calcium carbonate shell. And I don't want to go too far into the chemistry, but in seawater, a molecule of carbon dioxide is actually released for each molecule of carbon that goes into forming that carbonate shell. But cultivated shellfish, they're cultured in water and then removed from the system and used for other purposes. So the net carbon effect of shellfish products really depends on the use of that shell byproduct. They can be an abundant, cheap, sustainable resource that can be used in industry and construction. Some uses have carbon sequestration benefits and reduce the need for things like energy intensive mining, but other uses would actually lead to a release of stored carbon. So although shellfish aquaculture may sometimes have a net benefit, the overall effect, in total seems to be marginal. But more studies are really needed to direct the industry forward with regards to climate and the use of these industry byproducts. Additional potential impacts really depend on shellfish production, or the farm location, and combining the cultivation of shellfish and seaweed. So the cultivation of seaweed downstream of those shellfish increases the light availability for photosynthesis and reduces the load of epiphytes that tend to grow on farm seaweeds, which lowers the quality of the seaweed product. So that's one potential benefit, but there may also be negative effects if they're co-located with other blue carbon ecosystems like seagrass meadows. But those emissions and associated impacts on other blue carbon ecosystems haven't been evaluated for Oregon. I'll finish up pretty soon, but the carbon benefits, again, of aquaculture really depend on the types and practices used, whether those products produced replace others generated using really carbon intensive practices. And speaking generally, seaweed aquaculture appears to have the lowest emissions, where shellfish is slightly higher, and the aquaculture of finfish like salmonids really generate several orders of magnitude more carbon emissions than those other two. So to summarize the key takeaways, it's important to preserve existing ecosystems for carbon storage and biodiversity. Estuary-based restoration using existing methodologies is practical, and it really does enhance carbon sequestration. Restoring tidal flow is key to reduce those emissions, and that usually happens anyway in tidal restoration. Importantly, site-specific evaluations are needed for these precise estimates of carbon benefit. And restoration of scrub shrub tidal wetlands should be emphasized because of their fast growth rates and rates of carbon sequestration. Well, the carbon benefits really accumulate on a decadal scale, and it takes time to see those benefits. In terms of marine blue carbon dynamics in the nearshore ocean and kelp forest really need to be studied. Questions around the possibility and benefit to manage marine vertebrates as a carbon resource, but it's a question we should look into. And there's climate potential from aquaculture if those practices provide a net emission reduction. So I want to take a moment to thank folks at the Nature Conservancy in Oregon and Oregon Sea Grant for their generous support of my fellowship over the last year. My colleagues at TNC have been really incredibly supportive in contributing their time and energy to support this project. In particular, Rose Graves has spent many, many hours with me to write and shape the Blue Carbon Synthesis Report, and that should be available to share out very soon in the coming weeks. Additionally, Gina Carter was really the driving force behind this blue carbon work and designing the fellowship product. So I wanted to extend my thanks to all of those folks. And I appreciate all of you for taking the time to listen to me today. And I'm happy to take any questions, or if you'd like to email me, please send me an email at the bottom there. I can also copy it into the chat.
Great. Thanks, Joanna. That was awesome. I learned so much. Love this. Not just for everyone here watching, it's also for us to learn too. Okay. Question. Oh, somebody just popped something in there. Let's see. Joanna, you mentioned something about a blue carbon feasibility study in Oregon, but she missed what the subject of the feasibility was and where we might be able to access it. Can you explain a little bit more behind that?
Oh, sure. That was a feasibility study. Oh, I don't want to misattribute it. It's available on the Pacific Northwest Blue Carbon Working Group website. I can pull it up. I can provide a link for you.
Okay.
But it was looking into scoping finance projects in the Pacific Northwest.
Great, thank you. What do you think are like the biggest misconceptions about the topic of blue carbon? This is just my own question.
Oh, that's a good question. Maybe I should ask you that. Is there anything that you saw that was surprising?
I was surprised a little bit about the eelgrass information, and yeah, I guess I just didn't really know all the aspects behind that in terms of blue carbon.
Yeah, I guess what I would say is there's like sometimes a conflation between carbon benefits, natural climate solutions and sequestration rates versus what's creditable under a voluntary carbon market. And if you're overemphasizing the carbon markets, then sometimes you miss real benefits from generated from these really productive coastal ecosystems, because they don't follow the same rules or the standards that are set out for the ecosystem. And there's a really important part to that. Like, we don't want to provide carbon credits for carbon that we can't account for. But relying too much on those crediting schemes I feel like sometimes tends to miss the bigger picture in terms of carbon. But the other thing is we do want to focus more on, project effects. So there's a really good reason why those methodologies are set up the way they are.
Yeah. Okay, we've got another question for you from Grant. Not all kelp makes its way to the deep depths of the ocean to release its carbon. A lot washes up on the beaches to rot. So when kelp washes up on the beach, how much carbon is released back into the environment versus how much carbon is sequestered while the kelp is growing? It's a good question.
That's a great question. So a lot of the kelp that ends up on the beaches to decompose, that ends up right back in the atmosphere. While the kelp's growing, there is sometimes production of dissolved carbon that can make its way to the deeper ocean. Sometimes when drift kelp breaks off or is shredded into smaller pieces, those small pieces of kelp can make its way into deep ocean currents, which once you get under a certain depth, it can take decades to centuries for that material to return back close to the surface where it could be released. So there's a combination of ways that the carbon produced from kelp ends up either back in the atmosphere or into what we're considering carbon sinks, either ocean sediments or deep ocean currents.
Awesome. Does anyone else have any questions? Type it into the Q&A. Bob, do you have any questions for Joanna?
I do have a question. It's more kind of an overview question about, we get hit all the time with the idea that sea otters are little climate warriors because they will promote kelp growth and sequester more carbon and so on and so on. And sort of intuitively, that's probably true. But from your investigation, where are the big gaps in the actual data and knowledge or even techniques needed to quantify that to satisfy the basis of a carbon market? Yeah.
In terms of the sea otter effect or kelp?
Yeah, well, just kelp. I mean,
kelp.
Yeah, I mean, what are the key things that we still don't really know or that would enable us to otherwise start to frame a market around kelp and carbon sequestration?
Right. So the hardest part with kelp is being able to track the carbon from a particular site, a particular kelp forest to a carbon sink. And there's some ways we can do this in reverse. So we can look at sediments that have, a lot of organic carbon, and there's some techniques to establish the provenance of that carbon. So using DNA techniques, primarily I'm not sure if fatty acids is a way to look at that, but there are some, technical but expensive ways, time-consuming and expensive ways to look at the origin of that sediment carbon to a kelp forest. So at this point, we don't even really have great models for estimating the amount of carbon produced and exported. So we really need to have, just basic understandings of, the growth rate and extent of, to be able to look at the total production, and then be able to estimate, okay, this, X percent ends up back up on the beach where it rots, and, X percent makes it to ocean sediments, or back into the estuary. So there's a lot of the technicality, those technical aspects of being able to measure that carbon production and sequestration. It's just difficult right now. And it's a really exciting question. And I'm sure if we get enough smart people in a room, we can figure it out.
As long as we get the grant money to do it.
Yeah, exactly. We could figure out how to do it, but whether or not we could.
Well, thank you very much. Unless there's another burning question.
We've got a couple questions that just popped up. David asks, how deep does sediment need to be considered a sink?
Oh, that's a good question. That's a really good question. So the depth, I think it really depends on the system, because sometimes the carbon in the very surface of the sediments have enough oxygen to decompose. So really it's about the rates of decomposition. So in a lot of the estuary sediments, marine sediments, those are pretty low oxygen. So the sediments don't have to be that deep to be considered a sink. Yeah, I don't have much more to say about that, but it's a good question.
Yeah, I've got one more for you from Steve Rumrell. The ODFW Sea Corps team generates new updates to eelgrass maps for Oregon bays and estuaries. Currently, we conduct this work primarily to identify ecologically valuable habitat, nursery areas for fish and shellfish, special management areas in the estuaries, and so on and so forth. Question: is it premature for us to add carbon sequestration to the list of ecosystem services provided by eelgrass at a level that warrants the economic costs associated with the mapping work? Ooh, that was a lot.
Oh, so many great questions. I don't think it's too early to add carbon sequestration as to the list of ecosystem services. It may be framed more as a co-benefit rather than a primary, ecosystem action. But it really, to be able to know how much, carbon sequestration is happening because of eelgrasses, we need to know how much eelgrass there is, because it's, the rate depends on a per acre basis. I'm also realizing I saw in the chat that last question might have been referring to ocean depth. So yes, I'm agreeing that below 1,000 meters of water depth is a good ocean sink level. I think 500 to 1,000 is about where I've read.
Awesome. Okay, I think that's good for this presentation wrap up. Thank you, Joanna, for letting us know so much more information about blue carbon today. It was fascinating.